Welcome everyone to today's webinar. The topic is critical capacitor design considerations for cutting-edge C-UAS and drone defense applications. My name is Misha Piermai. I hold my bachelor's degree in electronics engineering and have worked in engineering, sales, and marketing roles in the capacitor industry for the past 13 years. During this time, I've helped a countless number of engineers specify capacitors for their mission-critical applications, including for counter unmanned aerial systems, or referred to as C-UAS. So during today's webinar, we'll start by going through a brief history of drones and how they've changed combat on the battlefield. We'll then discuss typical ways in which militaries counter the threat of drones and the critical role capacitors play in these C-UAS applications. We'll then review the different types of capacitors typically used in these applications and key selection criteria that engineers should consider when choosing a capacitor. Lastly, we'll conclude with a real-life case study. So, what is a drone? Now, a drone is an unmanned aerial aircraft that can be remotely controlled or fly autonomously using software-controlled flight plans in conjunction with onboard sensors and GPS. Drones are also known as unmanned aerial vehicles, or UAVs, or unmanned aerial systems, or UASs. Now, a weaponized drone is a drone that has been modified or designed to carry and deploy weapons such as guns, missiles, bombs, or other harmful payload. They can be equipped with various armaments, including firearms, such as handguns and rifles, explosives, like bombs and grenades, guided missiles, flamethrowers, and even chemical or biological agents. So then what exactly is drone defense? Now, drone defense, also known as counter-drone or counter-UAS technology, refers to systems and methods designed to detect, track, identify, and neutralize or destroy unauthorized or potentially threatening drones. The use of unmanned aerial systems, commonly known as drones, has become increasingly prevalent in military operations. The first significant military incident involving an effective drone attack is generally considered to have occurred on November 14th, 2001, during the early stages of the War of Terror in Afghanistan. A CIA-operated Predator drone entered Afghan airspace and tracked and neutralized a convoy carrying jihadi leaders. All of this was monitored in real time at CIA headquarters in Langley, Virginia. Now, drones provide weaker armies and terrorist groups with low-cost air power, allowing them to weaponize commercially available drones by attaching explosives or modifying them to drop munitions on enemy targets. The economic disparity between expensive countermeasures and relatively inexpensive drones is stark. Deploying rockets and missiles costing hundreds of thousands or even millions of dollars to counter drones that cost only a few hundred or a few thousands of dollars quickly becomes economically unfavorable. The conflict in Ukraine has demonstrated the increased prevalence of weaponized drones, with tens of thousands of drones being used for intelligence gathering, disrupting formations, and striking enemy positions. Increasingly, commercially available drones are being modified for military purposes, providing drone access to smaller militant groups with limited funding. The rapid increased number of threats posed by drones has given rise to the field of counter-unmanned aerial systems, or C-UAS. Cost-effective, mobile, and high-accuracy defense C-UAS tools have become a critical part of the overall defense strategy, accounting for billions in spending from R&D to procurement. Now, there are various methods to counter weaponized drones. One method includes the use of radio frequency or RF jamming. Now, this disrupts the communication link between the drone and its operator. GPS spoofing sends false GPS signals to the drone. misleading its navigation systems and causing it to change course or land. Cyber takeover systems attempt to hack and assume control of the drone. Nets and net guns are used to physically capture drones without destroying them. Kinetic weapons are a type of projectile weapon that relies solely on its kinetic energy to inflict damage on a target without using any explosive, chemical, or radiological payload. Kinetic weapons rely on mass and velocity to achieve their destructive effects. Examples include traditional firearms, railguns, and coil guns. Now, the use of directed energy weapons is a newer but rapidly growing C-UAS tool, gaining significant interest by militaries worldwide. A directed energy weapon is a ranged weapon that damages its target with highly focused energy instead of the use of a solid projectile. The main types of directed energy weapons are high-power lasers, microwave weapons, particle beam weapons, and sonic or sound-based weapons. Directed energy weapons use concentrated energy to achieve its outcomes and are very inexpensive to use, of course, once they're up and operational. So on this slide, we have a few examples of some actual counter unmanned aerial systems available today. On the top, we have kinetic weapons, which include vehicle agnostic modular palletized ISR rocket equipment, otherwise known as Vampire. This system uses rockets to physically intercept drones. Coyote missiles, which are designed to physically intercept and disable drones. The Drone Hunter F700, an autonomous drone that physically intercepts other drones. And Skywall Auto Response, which uses a projectile to capture drones. Now, some directed energy weapons include Drone Gun Tactical, which uses electromagnetic interference to disrupt drone communications and control. Now, a very exciting and rapidly growing C-UAS is Leonidas, made by Epirus. This uses high-power microwave technology to disable drones. Recently, Epirus and General Dynamics have integrated Leonidas into General Dynamics Stryker armored fighting vehicles. And finally, we have ODDS, or Anti-UAV Defense Systems, which includes RF inhibition capability. It's worth noting that some systems available today have both kinetic energy and directed energy components. So, what role do capacitors play? Now, capacitors have a variety of functions within C-UAS weapon systems. Some key functions include energy storage and delivery. So capacitors are crucial components in electronic systems for storing and rapidly releasing energy. In anti-drone weapons, capacitors are used to power high-energy electromagnetic pulse, or EMP systems. These can disrupt and destroy the drone's electronics. A capacitor's ability to rapidly release their energy makes them key in powering other directed energy weapons like lasers and microwave emitters. Another area, noise reduction or filtering. So capacitors help reduce electrical noise in circuits. In anti-drone systems, this could be important for improving the sensitivity and accuracy of drone sensing and detection equipment. Capacitors also provide voltage regulation. They help maintain stable voltage levels in electronic circuits. This is critical for ensuring accurate and consistent performance of anti-drone sensors and targeting systems. Capacitors also protect sensitive electronic components from voltage fluctuations commonly seen in these types of circuits. They're used on signal processing in applications including radar and other detection systems used to identify and track drones. And capacitors are also compact power sources. Advanced capacitor technologies like supercapacitors and hybrid wet tantalum capacitors are used for power holdup and power backup purposes to keep systems up and running during power interruption events. Now let's get right to the key decision criteria that engineers should pay close attention to when trying to choose the best capacitor for the job. Most C-UAS systems have one thing in common. They need to be portable. Comparing the energy density of different capacitor options helps ensure the most volumetrically efficient capacitor is chosen. A capacitor's energy density is the amount of energy stored in the capacitor per unit of volume. Higher energy density means that the capacitor is more volumetrically efficient or stores more energy in a smaller volumetric space. The energy density is calculated by dividing the energy stored in the capacitor by the capacitor's volume. The energy stored within the capacitor is determined using the equation E equals 1/2 CV squared, where E is the energy stored in the capacitor, which is expressed in joules, C is the capacitance rating of the capacitor, and V is the voltage rating of the capacitor. Once the energy stored within the capacitor is calculated, we divide it by the capacitor's volume to obtain the energy density. This is typically expressed in joules per cubic centimeter or joules per cubic inch. Supercapacitors are known for their extremely high energy densities, packing 10 to 20 farads per capacitor. However, their voltage ratings are relatively low, within the 2 to 10 volt range, requiring many to be connected in series to achieve usable voltages, which will reduce the overall energy density of the total capacitor solution. So it's important to understand the energy density of your capacitor solution. Now, power density, as we see on the slide here, is another capacitor attribute to truly understand, another capacitor attribute to truly understand. This is particularly important for higher power applications, which especially includes directed energy. Now, high power applications require a lot of energy to be delivered within a very short time frame. Directed energy applications such as radars, high power microwaves, and lasers have some of the most demanding power requirements in the industry. In addition, these systems must be compact, making them very sensitive to power density. Now, in order to calculate power density, we start by calculating the power using the equation we see on the slide, where power equals the energy we need to deliver divided by the time we must deliver it. As the required energy goes up or the time needed to deliver it goes down, the needed power is increased. First, designers must confirm if the capacitor can handle the application's required power needs, usually by checking the manufacturer's datasheet or even contacting them directly. Once confirmed, the power delivered by the capacitor is delivered by its volume to obtain the power density. Hybrid wet tantalum capacitors, made by Quantic Evans, are known for being the most power-dense capacitor in the world, and they are often compared to aluminum electrolytic capacitors, solid tantalum, and similar technologies. So size and weight are crucial considerations for C-UAS systems. As previously discussed, C-UAS systems need to be portable and lightweight to be effective. Choosing capacitors that offer the best performance while minimizing size and weight is essential for maintaining the system's overall efficiency and mobility. Having a true understanding of the energy density and power density of a capacitor option helps to ensure this is met. Now, the environmental conditions a capacitor faces when deployed are a key part of the selection criteria. Different capacitor technologies have different temperature ratings, so attention must be paid to the capacitor's temperature range during selection. Capacitors can have a maximum temperature ratings between 70 degrees C up to 300 degrees C, which must be considered. Some capacitors even require voltage derating above a specific temperature limit. Certain capacitor technologies have significant performance variations as the application's ambient temperature changes. For example, some capacitors have much lower capacitance ratings at cold temperatures, losing half or more of their rated room temperature capacitance at extremely low temperatures, which are commonly seen in avionics or space-based applications. Now, other capacitors, such as multi-layer polymer film capacitors made by Quantic Pactron, have very stable performance across temperature ranges due to their unique construction and materials. Shock and vibration withstand capability is another key component. Many C-UAS weapons expose their onboard components to high levels of shock and vibration while being fired or while traveling to their target. Systems mounted on ground vehicles or aircraft are also exposed to notable vibration conditions during transit to the battlefield. Shock and vibration affect various capacitor technologies differently, so these ratings need to be confirmed during the selection process. Some capacitors work exceptionally well in lab environments, but several ruggedized alternatives provide the needed electrical performance for use in harsh environments. Now, there are several MIL standards that specify shock and vibration tests designed to simulate the most aggressive field conditions, which capacitors are often designed to pass. Now, capacitors wear out or degrade over time, especially aluminum electrolytic capacitors, leading to decreased capacitance and potential instability. This wear out can occur while energized or during storage. Periodic inspection and replacement of some capacitor technologies are recommended to maintain optimal performance. Some capacitor technologies have an unlimited shelf life, ensuring they are ready even if the weapon has been in storage for an extended period of time. The equivalent series resistance, or ESR, of a capacitor is a major factor determining its suitability for use within a directed energy system. ESR is the internal series resistance that appears in series with the capacitance of the device. The ESR values range from a few milliohms to several ohms, resulting in power losses, reduced efficiency, and instability of power supplies and regulator circuits. Electromagnetic pulse, radar, and other similar directed energy applications work by means of a high current pulse. If the ESR of the capacitor is high, a lot of energy can be lost, typically in the form of heat. This phenomenon increases exponentially as the current increases, making these high current pulsing applications very sensitive to ESR. Now, surface mount device capacitors, or SMD capacitors, offer a low-cost, large capacitance to footprint ratio, while through-hole capacitors provide reliability under harsh environments due to stronger mechanical bonding. Some designers prefer the use of SMD capacitors, but not all capacitors technologies are available in this format. By considering these specific factors, designers can select the most appropriate capacitor for C-UAS drone defense weapons, ensuring optimal performance and reliability in countering evolving drone threats. So let's talk about some commonly used capacitor technologies available today. Film capacitors. So film capacitors offer high voltage, high energy discharge, and high ripple current capabilities. They are mechanically and electrically robust, self-healing with no piezo effect. There are many different types of film capacitors, including wound and stacked, the latter providing better inductance and lower ESR, offering an alternative to ceramic capacitors. These capacitors are commonly found on power supplies and communication equipment. Supercapacitors are known for their very high energy density. They are utilized in C-UAS systems that have significant energy storage needs. They offer stable performance over a wide temperature range and have been extensively tested for use in a variety of applications. However, the low voltage limits of supercapacitors present a challenge for applications greater than 10 volts. Supercapacitors are typically used where large bulk capacitance is needed, such as transmitting high power. Hybrid rectangular capacitors are somewhat similar to supercapacitors. They are known for their high energy density, but with an increased voltage range of up to 125 volts in a single capacitor. These are ideal for power holdup applications of power systems, TR modules of radars, and powering high power applications such as pulse lasers and electromagnetic pulse. Aluminum electrolytic capacitors come in a variety of shapes, sizes, and configurations, and they can be ruggedized to withstand harsh environmental conditions, including high vibration levels. They have a wide temperature range, commonly from -55 degrees C to 125 degrees C, and they provide stable and long-lasting performance in military and aerospace applications. Although less energy dense than hybrid wet tantalum capacitors in the low to medium voltage range, they tend to be a popular option for some power holdup applications and some voltage regulation circuits. Ceramic capacitors are indispensable in directed energy applications due to their high dielectric strength, fast response time, thermal stability, and reliability. They're used for energy storage, pulse discharge, filtering, and noise reduction, in addition to voltage regulation and forming resonant circuits, ensuring the efficient and effective operation of directed energy systems. Mica capacitors are commonly used in communications, radar systems, aircraft power supplies, and other military applications. They provide stable performance without cracking or piezoelectric effect, ensuring reliability in critical systems. Metal-clad mica capacitors utilize metal-clad technology. These capacitors run cool due to their silver-plated brass case that acts as a heat sink. They can carry high current with ultra-low resistance, making them suitable for RF and microwave power applications. By incorporating these diverse types of capacitors into C-UAS drone defense weapons, engineers can enhance the efficiency, reliability, and performance of their systems in countering evolving threats posed by drones effectively. Now, hybrid wet tantalum capacitors play a critical role in C-UAS drone defense weapon systems, particularly in defense electronics applications. So here are some specific applications of hybrid wet tantalum capacitors in C-UAS drone defense weapons. In power supplies, they provide power holdup, typically per mil standard 704 requirements, for stable and reliable power delivery to critical components. With munitions, they offer exceptional shock and vibration withstand capability and unlimited storage life for munitions-related electronics. In aerospace applications, they perform exceptionally well in these environments, handling high altitudes with a strong track record of success due to their high reliability and low MTBF. In military applications, they meet rigorous military specifications for mission-critical electronics and spacecraft, aircraft, and defense systems. They're used for decoupling AC signals, cleaning DC power, and bypassing and filtering. And finally, for pulse power applications, they provide that high current pulse that drives directed energy applications, such as radar, high power microwave, and high energy lasers. Now, hybrid wet tantalum capacitors offer several advantages that make them preferred components in specific C-UAS systems and applications compared to other types of capacitors. They provide a very high capacitance per unit volume due to their unique hybrid technology, providing a small form factor that meets the modern electronics compact size requirements. They have a very low ESR, reducing system losses and improving overall efficiency in electronic circuits within C-UAS systems. Their wide operating temperature range ensures reliable performance within the -55 to 200 degrees C range, making them suitable for harsh environments. They exhibit a low MTBF, or mean time between failure, making them ideal for mission-critical applications. They withstand high shock and vibration environments exceptionally well, enhancing the overall system robustness. They offer unlimited storage life and a very long operational life, making them suitable for mission-critical applications, particularly long life missions. And they handle repeated full discharges. They can be discharged repeatedly into a dead short without damage. Now, let's step into a real-life case study of an actual C-UAS application. An engineer had a circuit that required a minimum of 1,600 microfarads at 100 volts. Initially, an electrolytic capacitor was used to meet this requirement. However, each electrolytic capacitor was rated to 100 microfarads. Therefore, the engineer needed to use 16 of them, connected in parallel to achieve the needed 1600 microfarads. This solution had a total volume of 1.44 cubic inches. After speaking with me, I was actually able to offer a single hybrid wet tantalum capacitor that met that 100-volt requirement, and that single capacitor was rated to 2200 microfarads. This provided more capacitance in a volume of 0.61 cubic inches, which was less than half the size. Now, needless to say, the engineer was very excited about our conversation and, of course, how much space they were able to save with going with the hybrid wet tantalum capacitor option. Now, this appendix provides a quick summary of many of the key points we've discussed today. Feel free to take a screenshot or email us at info@quanticevans.com, and we'll be glad to send it directly to you. We're also available to discuss your specific C-UAS application and provide capacitor recommendations, even if it's a capacitor we don't manufacture. So this concludes my presentation, and I'd now like to open up the floor to questions at this time.
I do already have a couple questions here for you, Misha. The first one, so what is more important, power density or energy density?
Yeah, that's a great question. Now, that actually depends on the application. If your application requires a lot of energy to be stored, but it doesn't require that energy to be accessed quickly, then energy density would be the key parameter. If that energy needs to be accessed rapidly, like a high power pulse laser, then power density becomes far more important. Understanding both attributes helps to truly compare the capacitor options to ensure the most efficient option is chosen. But really, again, it's truly dependent on that application, the power needs of the application there. But again, a great question.
Next question I have, how supercapacitors really compare to hybrid wet tantalum capacitors?
Oh, yeah, another good one. All right, so there's two big differences between supercapacitors and hybrid wet tantalums. Supercapacitors, as I mentioned before, are very high in capacitance, but they're relatively low in voltage. So let's think of an example. If we're trying to use a 1 farad 5-volt supercapacitor in an application, let's say the application requires 50 volts. We need to connect 10 of those supercapacitors in series to achieve this 50-volt voltage rating. The problem with doing that, every time we add a capacitor in series, we reduce the overall capacitance of that so-called capacitor bank. So by the time we've connected 10 of these 1 farad capacitors in series to reach our 50 volts, we're down to 100 millifarads. Let's take that example with a hybrid wet tantalum capacitor. So a single hybrid wet tantalum capacitor, we can offer about 65, 66 millifarads at 50 volts in one capacitor. So to meet that 100 millifarad requirement, you could connect just 2 hybrid wet tantalum capacitors in parallel, and we'd actually exceed the capacitance rating of 10 of those 1 farad supercapacitors connected. So hybrid wet tantalum capacitors, they have their sweet spot, and within that range, within that sweet spot, they're the most volumetrically efficient capacitor option available today in the market.
So with that, I just want to thank everyone for attending today. As Misha said, you can learn more by visiting quanticevans.com or contacting Misha directly, whether you have questions about the webinar or about Evans capacitors, or receiving the best practices checklist at misha.piermike@quanticevans.com. You can also learn more about upcoming webinars from Quantic Electronics at quanticnow.com/thegrid. Thank you so much for joining, everyone, and have a great day.